Welcome back to CSConnect series. We are in number systems. This video will be dedicated to complements. What is the use of complements? We have seen about subtraction operation in arithmetic operations video, and we have hinted something like it's a bit complicated to do that process. So these complements are going to simplify the subtraction operation. Along with that, they are also used for logical manipulations, which we will see later. What are the types of complements available here? There are two types. One type is called r's complement and the other type is called r-1's complement. With regard to the decimal numbers, there are two kinds of complements. One will be the tens complement and the other will be nines complement. If you take r to be 10, then r-1 will be 9. Similarly, for the binary numbers, we have two complements here. One is the 2's complement and the other is the 1's complement. If we take r to be 2, then r-1 will be equal to 1. First, let's understand what is r's complement. So this complement video will be completely dealing with positive numbers. There is a separate topic for dealing with negative numbers. Say for example, signed numbers, whether it's plus or minus, that's a different topic. We will see that later. As for this video, we will just concentrate only on positive number. So let's take a positive number, capital N. And there is a base r. That r can be either 10 or 2. So whenever we consider any decimal system or binary system, we have two parts of the number. One part is the integer part and other part is the fraction part. Now we are only considering the integer part. It has n number of digits. Say for example, when I have a number 1, 2, 3, 4, how many digits does this number have? It has 4 number of digits. Count 1, count 2, count 3, count 4. When I say 999, how many number of digits are there? There are 3 number of digits. So we have to take the n digits from the integer part. How do we find the r's complement? We have to take the base and raise it to the power of number of digits n and then subtract it from the positive number capital N. This is the case when the number is not equal to 0. What about the case where the number is equal to 0? We can say r's complement is simply 0. Now let's see few examples from tens complement and 2's complement. First we will take tens complement. Tens complement of 52520. So when we spell it out, we will say 52,520 to the base 10. Now just get details from this. How many digits are there? 52520. There are 5 digits. So we are marking it as n is equal to 5. This particular n. So we will just separate it 52520. So there are 5 number of digits. You need not worry about the repetition of numbers. We are just worried only about the count of the digits. Now we have to take r power n. Here r is equal to 10 for tens complement and n is equal to 5, which will give 10 power 5. So 10 power 5 minus the number itself. So minus 52520. What is 10 power 5? We have 1 here and 5 number of zeros. We'll just do a subtraction now. There are 5 numbers of zeros, 52520. So what is the logic behind the tens complement? Whatever number of digits is there, that number of zeros should be present along with a 1 in the front. So this is the case. Just subtract it. 0 minus 0 is 0. Then we have 10 minus 2 is 8. Since we borrowed 10, this becomes 9. 9 minus 5 is 4. Then again we have 9. 9 minus 2 is 7. Then we have 9. We have 4 and this is 0. 47,480 will be the answer. So tens complement is you have to subtract the particular number from base to the power number of digits. We will see another example which has only the fractional part. Tens complement of 0.3267. Here how many digits are there in the integer part? After the decimal part you have 4 digits. But you have only 0 point here, which says n is equal to 0. That is, there is no integer part. You should not count the fractional part. Only the integer part has to be counted. Now r is equal to 10 and n is equal to 0. So 10 power 0 minus 0.3267, we are writing the number here. 10 to the power 0 is equal to 1. So 1 minus 0.3267. Let's subtract it. We have 0.3267 and so we will add zeros here. 1.0 and 1 are same only. So let's subtract. 10 minus 7 is 3. 9 minus 6 is 3. 9 minus 2 is 7. 9 minus 3 is 6 and 0 minus 0 is 0. So 0.6733 will be the answer. This is how you have to manipulate fractional numbers. What happens when there are integer part as well as fractional part? Here also the count will be taken for the integer part alone. So the integer part count is 2 digits are present, 2 and 5. Now the base is 10 and the power is going to be 2. So 10 power 2 will be coming here. 10 power 2 minus 25.639. This will be 100 minus 25.639. 100.000, 25.639. Just subtract. These are all normal subtractions. 10 minus 9 is 1. 9 minus 3 is 6. 9 minus 6 is 3. The decimal point. 9 minus 5 is 4. 9 minus 2 is 7 and this will be 0. 74.361 will be the answer. This is how we have to calculate tens complement. Now we have seen r is equal to 10. What about r is equal to 2? It has the same rules. So whenever they ask something in tens complement, you can understand it's for decimal digits. And whenever it's 2's complement, you can understand it's for binary digits. Obviously, this will have 9's complement and this will have 1's complement. 2's complement of 101100 to the base 2. How many digits are there? 1, 2, 3, 4, 5, 6. So here we have to take n is equal to 6. And what is the base? It is 2. If r is equal to 2 and n is equal to 6, this will result in 2 power 6. We have already seen that 2's complement is going to deal with binary. And here it is 2 power 6. That's why it is marked with the base decimal 10. Now let's take 2 power 6, find what it is and convert into binary. 2 power 6 is equal to 64. So let's take 2 into 2 into 2 which is equal to 8. 8 into 8 will give 64. 2 power 3 is actually 8. So 2 power 3 into 2 power 3 will give you 2 power 6 which is equal to 64. Now you have to find the binary equivalent of 64. Let's take 2 power 0, 2 power 1, 2 power 2, 2 power 3, 2 power 4, 2 power 5. This is 1, 2, 4, 8, 16, 32. We'll go for 2 power 6. This is 64. So when I want to represent in binary, I have to mark 1 here and the remaining places will be 0. So this is the representation. 1, 2, 3, 4, 5, 6. 6 numbers of zeros. So 64 to the base 10 can be expressed as 1, 000, 000 in binary form. Now you have to apply this part in the first place. Let's start subtracting. 0 minus 0 is 0. 0 minus 0 is 0. What happens when 0 is less than 1 but it is given in the difference? We have to borrow from the previous one. 1 is present only here and in between you have only zeros. What you have to do is you have to borrow 1 0 here. This will become 0 and automatically every digit here will become 1. You are borrowing 1 from here. So this is becoming 1 0. That is the representation of 2. You have to change the preceding 1 to 0. But you don't have any ones in between. You have 3 zeros in between. So every zeros will be converted to 1. The preceding 1 will turn to 0. So as per rule, when you get 0 to 1 0, the preceding 1 should change to 0. This is the rule. But what about the in-between zeros? Everything will be converted to 1. So what is 1 0 minus 1? It is 1. What is 1 minus 1? It is 0. What is 1 minus 0? It is 1. What is 1 minus 1? It is 0, and 0 minus 0 is also going to give 0. So the answer will be 10100. So it actually starts from here, but I have included even the first digit and written in this way. 2's complement of the given number is 10100. Now we'll see another example which has the fractional part. Here the integer part is going to be 0 because we have 0 point the fractional part. And what is the r here? R is 2. So 2 power 0 to the base 10 minus the given number. 2 power 0 is 1 and 1 in decimal is equal to 1 in binary. So we are just keeping it as 1. Now we have to go for subtraction. What is 0 minus 0? It is 0. Then we have to go for borrowing. Let's take 0, 1, 2, 3. This is 0, 0, 0, 1, 1, 0, 1, 1. This becomes 1, 0, and so the remaining zeros become 1 here, and this 1 turns to be 0. 1, 0 minus 1 is 1. 1 minus 1 is 0. 1 minus 0 is 1. Retain the decimal point. 0 minus 0 is 0. 0.1010 will be the right answer. This is the 2's complement of the given value. This is how we have to do 2's complement. Let's go to the r minus 1's complement. Here also we have a positive number n and a base r. Here we have to consider both the integer as well as the fractional parts. So the integer part digits will be counted as n and the fractional part digits will be counted as m. R minus 1's complement is given as, when there was only integer part considered in R, it was R power n. Here we are considering both the integer part as well as fractional part. So we have to include R power m also. So this will be R power n minus R power minus m minus the given number. So if R is equal to 2, we have R minus 1 is equal to 1, which says 1's complement. When R is equal to 10, then R minus 1 will be 9, which is the 9's complement. The R minus 1's complement of a number in base 11. How do you take it? If R is equal to 11, then R minus 1 will be 10. So why is this statement irrelevantly coming in this context? It means you can get a number in any base and they may ask you to find the R minus 1's complement of that base. There is a practice problem related to it, you will understand there. Let's get into 9's complement. We are going to consider the same number for 9's complement and 1's complement that we discussed in 10's complement and 2's complement. So let's have the positive number 5 to 5 to 0. So here the number of integer digits will be n is equal to 5 and the fractional part is 0, so m is equal to 0. Now r power, what is r here? R is 10. Understand, you should not take r to be 9. R is equal to 10 and we are going to find r minus 1 which is equal to 9. So r minus 1 is 9, r is 10. So this will be 10 power 5 minus 10 power 0 minus the given number. What is 10 power 5? It is 1 with 5 zeros minus 1. What is 1 with 5 zeros minus 1? 10 minus 1 is 9. Then remaining all digits will be turned as 9 and this will be 0. So write all the 9's here. Now you will have 5 number of 9's. What logic can you understand from this? When we had 5 number of digits, we used 1 and 5 zeros. Here when there are 5 number of digits, we are using 5 number of 9's. You can simply understand, count the number of digits and have 1 9 for each digit. So let's take 5 9's here. 5 2, 5 2, 0. So let's subtract it. 9 minus 0 is 9. 9 minus 2 is 7. 9 minus 5 is 4. 9 minus 2 is 7. 9 minus 5 is 4. 4 7 4 7 9 will be the answer for the given numbers 9's complement. The next example with the fraction part. Here n is equal to 0 and m is equal to 1, 2, 3, 4. Now this will be 10 power 0 minus 10 power minus 4. So this will be 1 minus 0.0001. Just understand this, 10 power 0 is equal to 1. What is 10 power 4? It is 1 with 4 number of zeros. When you take this to the numerator, this becomes 10 power minus 4. It means after the point, there are 4 number of digits with a 1. So this can be written as 1 into 10 to the power minus 4. So let's subtract this. You have 10 here, this becomes 9 and every other 0 will become 9 and this one changes to 0. So this is 4 number of 9 with a point. Now what do you understand from this part? If I have 4 number of digits in the fractional part, then you have to subtract 4 number of 9s in the fraction part. So when it was integer, for a 5-digit number, we used 5 number of 9s. When it is for the fractional part, there are 4 fractional digits and so we use 4 number of 9s after the decimal point. So now we have to subtract this 0.9999, 0.3267. Just subtract them. 9 minus 7 is 2, 9 minus 6 is 3, 9 minus 2 is 7, 9 minus 3 is 6. 0.6732 will be the right answer. Now what about the example which involves both the integer as well as fractional part? Without even going by this particular format, we should say we have to subtract 25.639 from 99.999. This will be the idea that you have gained in previous 2 examples. Now let's check that. We have n is equal to 2 for integer and m is equal to 3 for fraction. It is going to be 10 power 2 minus 10 power minus 3. 10 power 2 is 100. 10 power minus 3 is going to be 0.001. What is 100 minus 0.001? This is going to give 10 minus 1, 9. Then everything is going to change to 9. So we have 999 after the decimal point. Here also we will have 9 and this one is changed to 0. So we have 99.999, 99.999 and 25.639. Just subtract this. 9 minus 9 is 0, 9 minus 3 is 6, 9 minus 6 is 3, the decimal point. 9 minus 5 is 4, 9 minus 2 is 7. We are getting 74.360. This is how we'll be working with a number that has both the integer part as well as the fractional part. So if you compare 10's complement and 9's complement, you can find 9's complement a bit easy because you are going to subtract everything from 9's. Now let's get into the 1's complement. So if r is equal to 2, r minus 1 will be 1. So whatever representation here they have given in r will be taken as r is equal to 2. The 1's complement of 1 0 1 1 0 0 is. So here we have n is equal to 1 2 3 4 5 6 and m is equal to 0 because there is no fractional part. So let's have n is equal to 6 and m is equal to 0. So how will this be taken? This is 2 power 6 minus 2 power 0. So this will be 2 power 6 is 64 and 2 power 0 is going to be 1, which means 64 minus 1 will give you 63 here. So you are going to subtract this from 63. What about 63? Let's take 2 power 0, 2 power 1, 2 power 2, 2 power 3, 2 power 4, 2 power 5 and 2 power 6. This is going to be 1, 2, 4, 8, 16, 32 and 64. When this is going to be 64, the remaining digits will make up to 63. 32 plus 8 will give you 40. 40 plus 16 will give you 56. 56 plus 4 will give you 60, 62 and 63. All together every other digit will give you 63. Only then for 64 you can place a 1 here. So how will we do this? We have to place 1 in every other place. So 6 number of 1s will give 63. So 2 power 6 is 64. 2 power 6 minus 1 is 63. 63 can be represented in binary as 6 numbers of 1s. So understand we have 6 number of 1s. This is going to be 2 power 0 1, 2 power 1 2, 2 power 2 4, 2 power 3 8, 2 power 4 60, 2 power 5 32. 32 plus 16 is 48. 48 plus 8 is 56. 56 plus 4 is 60. 60 plus 2 is 62. 62 plus 1 is 63. Only when you change all these to 1, you will be having 1 and 6 numbers of zeros for 64. Let's get into the subtraction part. 1 minus 0 is 1. 1 minus 0 is 1. 1 minus 1 is 0. 1 minus 1 is 0. 1 minus 0 is 1. 1 minus 1 is 0. 0, 1, 0, 0, 1, 1 will be the answer. What do you find here? When you subtract every binary digit from 1, you get the other digit. When you subtract 1 and 0, you get zeros another number. When you subtract 1 from 1, it becomes 0. This is going to be the number n. Wherever you had 0, it is changing to 1, and wherever you had 1, it is changing to 0. So now the logic behind 1's complement is invert the bits. Wherever you have 0, place 1. Wherever you have 1, you place 0. So this is the answer. 0, 1, 0, 0, 1, 1. 1 has changed to 0. 0 has changed to 1. 1 as 0, 1 as 0, 0 as 1 and 0 as 1. Let's now see an example of fractional part. Here there is no integer part, so we will have n is equal to 0, and in the fractional part we have 1, 2, 3, 4. 4 digits, so m is equal to 4. We have to express this as 2 power 0 minus 2 power minus 4. And this part is completely in decimal. 2 power 0 is going to be 1. 1 minus, how will we write 2 power minus 4? This can be written as 1 by 2 power 4. What is 1 by 2 power 4? It is 1 by 16. So we will substitute 1 by 16 here. This part will become 16 minus 1 by 16, which is equal to 15 by 16. So 15 by 16 is converting to 0.9375 and still it is in decimal. So 15 divided by 16. This is going to be 0.9 and this is 144. We have 6, 3, we have 48, then we have 120, 7, this is going to be 112, then we have 80, 16 5s are 80. This is how we got 9375. It's a simple division process. Now we have to convert this decimal to binary. What should we do? We have to multiply the fractional part by 2 till fraction becomes 0. Let's start multiplying. 0.9375 into 2 will give 1.875. Keep the integer as it is and then use the fraction for further multiplication. 0.875 into 2 will give you 1.75. Keep the integer part, take the fractional part for multiplication. 0.75 into 2 is equal to 1.5. 0.5 into 2 will give 1.0. Now you have 0 in the fractional part, which means you have to stop it with here. Now just take the output. You have 0.1111. This is just similar to 9's complement, where every number has to be subtracted from 9. Here the case is every number has to be subtracted from 1. Let's go for the subtraction part. 1 minus 0 is 1. 1 minus 1 is 0. 1 minus 1 is 0. 1 minus 0 is 1. So 1 0 0 1 after the decimal point will be the answer. Now just invert this part. This is going to be 1, this is going to be 0 and this is going to be 1. And people can ask me, what about this 0? Since the fraction is given here, this 0 is not going to be counted. We have learnt about 10's complement, 9's complement, 2's complement and 1's complement. Now using 9's complement, we will try to get 10's complement. Similarly, using the 1's complement, we will try to get the 2's complement. Why are we using r minus 1 to get r? In 9's complement, you subtract everything from 9. Similarly, in 1's complement, you are just converting the 1 to 0 and zeros to 1. If you are using this answer to obtain the 10's complement and this answer to obtain the 2's complement, this is going to simplify the work that you are doing. So let's see how to do that. 9's complement is obtained by subtracting every digit from 9. How do we get 10's complement? Just add 1 to 9's complement, you will get the 10's complement. What about 1's complement? We are changing all the zeros to 1's and 1's to zeros. Then how do we get the 2's complement? Just add 1 to the 1's complement. So when you have 9's complement, just add 1 to get 10's complement. When you have 1's complement, just add 1 to get 2's complement. This is how it is getting simplified. If you go and see the sums, example for 52520, for 10's complement, it would have given some answer 47480, I suppose. When you take 9's complement, it will be 47479. If this is going to be the 9's complement answer, when I add 1, I automatically get the answer that is needed for 10's complement. If I have a number named n and I am going to take n's complement, if I take the complement of this value, it will again give n. Let's take r's complement of n to be r power n minus n. Now we have to find the complement of this number. Complement of this number will be r power n minus the complete number. So r power n minus n's complement will be r power n minus the complete number. Just apply the minus inside. This will be minus r power n and this will be plus n. Now r power n can get cancelled and we have n. So complement of the complement will restore the number to its original value. Why are we doing all these process? Actually, in computations, computer cannot do all the calculation as we do in paper and pencil. Complements are the ways with which things are done in an efficient way. Let's get into the practice problems of complements. The first practice problem, find the 1's complement and 2's complement of the binary number. What we will do is we will stick to the simplified process. We will find the 1's complement and just add 1 to it to find the 2's complement. Let's take the binary number. We will find the 1's complement. So how do we find? We have to convert the zeros to 1's and 1's to zeros. So this will be 1, 0, 0, 0, 1, 1, 1. This is the 1's complement's answer. Now how do we find the 2's complement? Now we will take the 1's complement value, add 1 to it and then find the 2's complement now. 1 plus 1. So let's take 0, 1, 2, 3, 0, 0, 0, 1, 1, 0, 1, 1. What is 1 plus 1? It is 2. 2 has to be represented in form of 1, 0. So let's have 0 here and 1 here. What is 1 plus 1? It is again 1, 0. So 0 here and 1 here. What is 1 plus 1? It is 0 here and 1 here. What is 1 plus 0? It is 1. The 0 zeros can be written as it is and 1 can be written as it is. So 1, 0, 0, 1, 0, 0, 0 will be the answer. Now shall we check this in 2's complement form? What we will do is in 2's complement, we will take the number of digits 1, 2, 3, 4, 5, 6, 7. If there are 7 digits, it's going to be 2 power 7 and the value of 2 power 7 is 128. If 64 has 1 and 6 number of zeros, 128 will have 1 and 7 number of zeros. 1, we will have 7 number of zeros and then we have to write this number 000, 111 and 0. Just subtract this. 0, 0, 0. We have a borrow here and so the remaining places will change as 1. 1, 0 minus 1 is 1. 1 minus 1 is 0. 1 minus 1 is 0 and this is 1 minus 0 which is 1. Did you get the same answer? So instead of going through this procedure, we are simplifying it with this. So the 2's complement answer is 100, 100. The next question, find the 9's and 10's complement of the decimal number. We will take the decimal number and we will find the 9's complement first. So what we have to do is we have to subtract every digit from 9. What is the answer we get? 9 minus 0 is 9, 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 9 minus 1 is 8. Now we have to take the 9's complement and add 1 to it. What will be the answer? 9 plus 1 is 10, 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 1 plus 8 is 9. So this is the 10's complement. Shall we check it the other way? How many digits are there? 1, 2, 3, 4, 5. 5 digits are there, so it is 10 power 5 minus 10,000. Don't take this to be binary number. This is a decimal number and it is 10,000. They have clearly mentioned it as decimal number. Even decimal number has zeros and ones. So how many zeros should I have? I should have 5 zeros here for 10 power 5, and the given question has 4 zeros with a 1. Now just subtract 0, 0, 0, 0. This is 10, this is 0. 10 minus 1 is 9. Did you get the same answer here? Yes. So instead of taking a separate procedure for tens complement, we are going with the nines complement and adding 1 to get the tens complement. So this is the answer of nines complement and this is the answer of tens complement. The next question, we have to find the tens complement of a 11 base number. So if r is equal to 10, we said r minus 1 is equal to 9. For nines complement, we took the procedure of subtracting every digit from 9. When r is equal to 11, then r minus 1 is equal to 10. This has to follow the same process. For tens complement, we have to subtract every digit from 10. If you remember ones complement, we subtracted every digit from 1 in the long process that we saw. After subtracting every digit from 1, we found that zeros are converted to ones and ones are converted to 0. Similarly, in nines complement, we subtracted every digit from 9. This is also a r minus 1's complement with regard to base r. So if r is going to be 11, r minus 1 is going to be 10. So which procedure it should follow? It should follow r minus 1 procedure. As per r minus 1 procedure, for ones complement, we are subtracting every digit from 1, and nines complement, we are subtracting every digit from 9. Here the case is when r is equal to 2, this was found using 1 minus. When r is equal to 10, this particular nines was found by subtracting from 9. Similarly, when r is equal to 11, we have r minus 1 as tens complement. So what we should do? We have to subtract from 10. So understand the question. When they ask you to find tens complement of a decimal number, you have to apply the procedure what we have been seeing in the example of r's complement. But here, when they say tens complement of 11, here r is 11 and r minus 1 is 10. You have to understand this question in the correct way. That is why I included this problem purposely. So nines complement of decimal number is nines complement of base 10. Here r is equal to 10 and r minus 1 is 9. So here they are asking for tens complement of base 11. It means the procedure of this nines complement has to be followed with respect to 10. So in that case we are concluding for tens complement we are going to subtract every digit from 10. Now let's take the base 11 number 935 as given in the question, and now let's subtract from 10. What is the tens complement? 10 minus 5 is 5, 10 minus 3 is 7, 10 minus 9 is 1. The tens complement of base 11 number 935 will be 175. So understand this, whenever they say decimal number, r will be 10, r minus 1 will be 9. When they say it's a binary number, r will be 2, r minus 1 will be 1. When they say a base r number, then this is going to be r, this is going to be r minus 1. Here r is 11 means this is 11 and this is 10. So we have covered r's complement and r minus 1's complement in this video. In r's complement we discussed tens and 2's complement. Similarly in r minus 1's we discussed 9's complement and 1's complement. I'll meet you in the next video. Thank you viewers.